Okay, so it should be live now, and it is 11:50, so let's get started. Our first problem today is on Venn diagrams. So we're checking if the following property is true. I'll let all of you work on this one for a minute, and then we'll go over the answers together. So I'm just going to set a timer for 2 minutes. All right, that is about 2 minutes, so let's get started. We've got 3 Venn diagrams for each side because there's about 3 steps for each side of the equal sign. So we start by writing B union C because that's the first term in our left-hand side. And we know that B union C is everything that's in C and everything that's in B. All right, and then our next term is going to be A, and that one's not too difficult, just everything that's in A. So this one really gets tricky on our last step. We've got B union C subtract A. So I've got some diagrams down here. Go ahead and put in the chat which number looks the most like what you got for your Venn diagram. Seeing lots of ones? Awesome. Yeah, that's going to be B union C, subtract everything that's in A. Oops, that's the wrong pen. So it's just everything that was in our first diagram without anything that was in the second diagram. All right, now the main goals here is to try and figure out whether these are equal. So let's go through the right-hand side. And our very first term is going to be B minus A. This is another one of the tricky subtraction ones. So down here, again, just go ahead and put in the chat which one looks like B minus A. Okay, yeah, 2. So, whoops, went too far. So we've got everything that's in B, but we don't include A. Now it's going to be pretty similar for our second step, C minus A. We'll have everything that's in C that is not in A. And then for our very last step, we want to find the union of them. And the union is just everything that is in both of our first diagrams. And when we fill that in, we can see that it is going to be equivalent to the left-hand side. So we don't need to find a counterexample for this one. All right, are there any questions on that problem? Okay, then we will move along. So this is going to be our, we're looking at a set proof, and this is going to be an element-wise proof. So I'll let you all work on this one as well, but just a reminder that our starting point and ending point is going to be first that we let some element be in the set on the left-hand side. And eventually we want to prove that this element being in the first set implies that it's going to be in the second set. So now that you have like a clear picture of the goal here, I'm going to give you 3 minutes to work on this one, and let me know in the chat or raise your hand if you have any questions. All right, just about a minute left to work on this one. Okay, that is 3 minutes. So let's work through this together. So we've got that X is in the set of A union B intersect C. So that means we know that that by definition of union and intersect, that X is going to be in A or X is going to be in B intersect C. So when we see this or, what does that mean? What's our next step?
you do two cases then?
So our first case, let's let X be in A. And remember that we're trying to prove that X is in this right-hand set. So we notice that A is unioned. I'm not sure the verb for that. It's joined with B and C, and by definition of union, if X is in A, then that means X is in A union anything. So that means we know that X can be in A union B, and X also can be in A union C. So now we've got another keyword here, and what does that tell us? All right, so the and, especially when we're working with sets, is going to tell you that if something is in one set and another set, then by definition of intersection, X is going to be in both of those sets. So we've shown that X is in fact in that right-hand set. We're not done, we still have that second case, which is that X is in B intersect C. So what can we say about X?
By definition of intersect, the X is in B and C.
So by definition of intersection, X is in B and X is in C. And this is basically the same property that we applied right here. We're just going the other way. So we've got the X is in B, X is in C. What is a property that we can use to, what's a property that we can use to get to our ending point? I'd love to hear from somebody new on this one. I'll give you a hint. It's similar to what we did for the first case. Okay, so remember that we're trying to show that X is going to be in both of these two sets. We've got the X's in B, we've got the X's in C. So what's next that we need to prove so that we can say that it's in both of those two sets?
Prove that X is in A.
And we can use the same property as before, that by the definition of union, that means that X is in B union A and X is in C union A. We can also hurry and use the commutative property right here, because we know that that means X is in A union B and X is in A union C. And now we can take that last step and once again use our definition of intersection to say that X is in A union B and X is in A union C. So we've shown that X is in A union B implies, X is in A union with B intersect C implies that X is in A union B intersect with A union C. So this is where you just want to put a quick conclusion saying, like, here, let's move this down actually. So we're just going to say, since we know that this is true, and you usually want to reference in both cases. Then by definition of a subset, A union with B intersect C is a subset of A union B intersect A union C. All right, are there any questions on that process, how we did that element-wise proof?
Where did you get that in case 2 that X was an element of A union B and X was an element of B union A and X was an element of C union A?
Yeah, so that just came from this property that we used up here. It'd probably be good to specify it in your proof. I was just trying to go a little bit quicker, but if X is in A, oh goodness. If X is in A, then X is in A union anything, right? By definition of union, as long as it's in one of them, then it's going to be in the union of both of them. So it's a similar property that we used in the first case. We're just using it for B and C this time.
So for example, we're saying that, but in case 1, we're saying that X belongs to A, and in case B, we're saying that X belongs to B intersect C. So do we bring case 1 into case 2 then? Like I'm
Not
saying.
quite. It's just using the same property. So here, this might make it a little bit clearer. I'm just going to move all of this down a little bit. So if X is in B, that implies that X can be in B union with any other set. Because if we had our Venn diagram here and we had, let's just say, oh, those are ugly circles. Let's try that again. Let's say that this is A and this is B, then if X is in, actually, let's just highlight. So this is B union with A. And if X is in B, that means that it's going to be in B union with anything. We could have C here and it would still be in the union, because the union is just everything that's in B and everything that's in C together. It doesn't eliminate any elements. Does that make sense?
Yes, thank you so much.
All right, any other questions? All right, let's move on. We are trying to prove using all of these properties that A union with A complement intersect B is equivalent to A union B. So let's write the starting and ending point for this one again. A union A complement intersect B, and we're trying to show that it equals A union B. So we're just gonna work through this one as a class, and I would love to have a different volunteer for every step of the process. So is there someone who wants to take a stab at what the first property we're gonna use is?
Distributive.
So we can use this distributive property. Oh, whoops. That is associative. That one. There we go. And we can say that A union with A complement intersect with A union B. And you want to cite, we used the distributive property. All right. Any volunteers for the next step?
Negation.
Negation, awesome. So negation says that A union with A complement is the universal set. So we can put in a U right here and intersect it with A union B by the negation. All right, what is next? Make sure that you're
Commutative.
not skipping any steps here.
Commutative.
Yeah, awesome. So we want to say A union B intersect with the universal set using commutative. And does anyone want to say why we did that? It's because we did it to use another property. So what's the next property that we want to use?
Identity.
So let's see, where did it go? There we go. So we know that anything intersect with the universal set is just itself. So let's move this up here. And we got this from the identity. And now we've finished the proof. Are there any questions on that one? It's really similar to the ones that we did with propositional logic, so. All right, we'll keep going. Oh, whoops, okay, 1 second. Forgot to clear this one out last night when I was practicing. Okay, there we go. All right, oh, whoops, is it still showing it on there? Gosh. Okay, I'm not sure why it's still, is it showing it on your screen share when I scroll down?
Yes.
Okay, I don't know why it's doing that. So we're just gonna use this space right here, right above it instead. All right, so we're trying to prove that this statement about sets. So I think the easiest way to do it is to start by just naming these to be A, B, and C. That makes it a little bit easier. And then it just becomes really similar to our element-wise proofs, where we say, okay, X is in A intersect B, and we're trying to show that that implies that X is in C. So I'm going to give about 3 minutes to work on this one. And again, just let me know if you have any questions while you're working on it.
If we're showing that like one element is in an element of another set, is it fine if we like give her like an example with a number to show that they are in the same set?
So that would be a proof for that one specific number, but in order for it to prove it for every case, it's best to use an element-wise proof.
Okay.
All right, that's 3 minutes. So it's totally okay if you haven't finished yet. We'll just work through it together. So we started with X is in A intersect B. What does that tell us about X?
X is in A or X is in B.
Really close. So X is in A and X is in B. And because we've got formulas for this one, then that also means that X is equal to n squared minus 1 and X is equal to 2k. Does anybody know where we can go from here? Anybody that I haven't heard from today? So there's a substitution we can make.
Do you plug in 2k into n squared?
So do you mean plug in the 2k for the n or just?
Yeah, 2k for the n.
So not quite, because we don't actually know that 2k equals n, we just know that x is equal to both of them. So we can set n squared minus 1 equal to 2k. All right, and if we rearrange, let's see, also by substitution. So let's rearrange and we can see that n squared equals 2k plus 1. This form should be pretty familiar. What does this tell us about n squared?
It's odd.
So n squared is odd. And we also, this isn't, it would probably be more specific if this were on a homework or a quiz, if we can use this property, but we are given that if a number squared is odd, then that means that n is also odd as well. So if n is odd, does anybody want to say what they wrote down n was equal to? You can also put it in the chat. So this is just going to be, we're just going to be using our properties of odd numbers. So by definition of odd, we can set n equal to what?
You could set it equal to like 2p plus 1, where p is an integer.
Yeah, awesome. Where p is in the set of integers. So now we can make that substitution from the first step. Now we can substitute, now that we know what n is, we can substitute that in. So we can say that x is going to be equal to 2p plus 1 squared minus 1. And that gives us 4p squared plus 4p plus 1 minus 1. And those ones cancel out. So then we can pull out a 4 and have p squared plus p. Whoops, not where. By factoring. And then I'm just gonna move us up to this side. Now we can use closure. So equals 4c, where c is in the set of integers, by closure. And now we've got that x equals 4c. So that means x has to be in the set C, because that's the same form that C takes. All right, so now we do a conclusion. We can use, once again, we use this. So that means that A intersect B is a subset of C by definition of subsets. All right, are there any questions on that one? I know that that was kind of one of the trickier element-wise proofs.
So I had a quick question. So because when it describes the set for C, it's for M, do we not have to make that M, or it can just like be any variable?
Yeah, it can be any variable. It probably would be good just to put an M. I could probably change that, but no, you're totally fine to use any variable because it's just that it's in the same form.
Thank you.
Yeah, because remember that these variables are just representing any number in this set of integers. So since C is in the set of integers and M is in the set of integers, essentially they're the same thing because they just represent any integer. Any other questions? Okay, let's move on to our next one. So this one is not quite, it's not going to be, we're not proving using these properties. We're just trying to rewrite the set inequalities, rewrite the following set equalities in Boolean algebra notation, just to get some practice with Boolean algebra. So I've highlighted this property down here that A subtract B is equal to A intersect with B complement. And that's going to be really important when you're rewriting this one. So I'm just going to give you, let's say, just 1 minute to work through this one, and then we'll go through it together. All right, that's 1 minute. So using this property, what can we use as the first step in this problem?
Complement and negation.
Yeah, so let's rewrite it. Does anyone want to volunteer what they rewrote the set to be? All right, let's go through. So we can keep the first term the same, A intersect B, but instead of writing subtract, we're just going to go intersect with B intersect C complement. And we're going to do the same thing on this side. Instead of subtract, we put intersect with C complement. Right, now this is in a form that we can translate to Boolean algebra pretty simply. And remember that intersect is going to be equal to the multiplication symbol in Boolean algebra. So we can write A times B times B times C, and we can still use the normal complement sign, equals A times B times C complement. And that's everything, that's Boolean algebra. So are there any questions on that one? Okay, so our very last problem is going to be looking at, actually this, I think, yeah, this is the last problem. We want to show that A, B, and C is a partition of the set of integers. So what are the three things that we need to prove to say that something is a partition? I'd love a different volunteer for each of these properties.
All the numbers are used.
Mm-hmm. So all of the set of integers is represented. Okay, what's another property? And you can put it in the chat as well.
No duplicates.
No duplicates, or another word for that is overlap. All right, what's the last thing? This one's easy to forget because it seems kind of obvious.
I think that there has to be more than one set.
Mhm. So there has to be, they have to be non-empty. So they have to have at least one element in them. So I'm going to move these first two down a little bit because non-empty is probably the easiest to prove. We basically just have to list one element. We just have to say this is an element in this set. So what's an element in A?
All even ints.
Yeah, so we can just say, let's just say 2. 2 is in the set of A, so it's non-empty. What's a integer that we've got in the set B?
5.
Yeah. 5 is in B, so it can't be empty. And one more for C.
7.
7.
7 is in C. So that means A, B, and C are non-empty. Awesome. Now for this proof, the second two are kind of connected. You kind of prove them the same way. Does anyone want to take a guess at about like the sketch that we're going to use to go through this?
Take the intersection of all those sets and show that's empty.
That is, it might work. It's possibly an overcomplication because of the specific properties that these sets take up. Because we already talked about A is the set of even integers, and B is 4k plus 1, and C is 4k plus 3, which is, those are, by the division theorem, those are divisions by 4 with a remainder of 1 and 3. So what we can kind of show from this, it's not as much a mathematical proof as it is like a reasoning proof, because we know that every integer takes the form, well, and every integer is even or odd. Do we all agree with that? So every integer is either 2k or 2k plus 1. So every integer is going to be in one of those forms. A represents everything that's in 2k. So A represents integers of the form 2k. And now this is where it gets a little bit tricky, right? So if some integer is divisible by 4, then it is divisible by 2. And this one in a formal proof, you might want to go through a like kind of a sub-proof off of that and say why that is true. But we're just going to say every integer of the form oops, 4k, or actually 4k plus 2 is even. Because if you add 2 to an even integer, it'll be even as well. So the only other forms are 4k plus 1 and 4k plus 3. And B and C represent those forms. So that proves, first of all, that there's no overlap. And it also proves that there are no duplicates, or that all of Z is represented, because we've got all even and all odd integers, and there's no overlap between them. So does that make sense? I know we've gotten used to doing like mathematical proofs, so it's kind of weird to not be trying to substitute stuff, but this is just using the properties of integers to make that proof.
Question. I know this might be like obvious or something, but so wouldn't B and C overlap?
That's definitely, it's not obvious. But the reason that we know that B and C don't overlap is because and this is true for basically because of the division theorem, we know that this 4k, 4k plus 1, 4k plus 2, and 4k plus 3, this is already a partition. This is a partition of all integers because we've got everything that's divisible by 4, everything that's divisible by 4 with a remainder of 1, with a remainder of 2, and with a remainder of 3. And that's going to be the case for every single integer. For 3, it's going to be 3k, 3k plus 1, and 3k plus 2. So since these are already a partition, we already know that there's no overlap there. Does that make sense?
Yes, thank you so much.
Any other questions about why this works? All right. So we got finished up a little bit early today. Feel free to take off if you'd like, but if you want to go over any other questions, any homework problems, we can help you out with that. I'll hang around. But you're dismissed.
I had a question regarding like the homework, like
Okay.
the number of the problems. So like we just downloaded the template, but there's like 13 problems in the overview, but there's only 11 in like the actual ones that are as part of it. Do we have to like include those problems somehow, like editing the PDF, or do we just ignore it?
Sorry, just one second. I'm going to stop my screen share so that I can look at this assignment. I did not notice that. Let's see. Let me just hurry and check.
Which one are we talking about?
We are talking about homework 3. I just barely realized. So the very front page I'm not even sure. Let's see, 11 says 15E.
I mean, what does like Gradescope say for the questions we need to like match them to?
I will check that right now. Let me see if I can pull that up real quick. Sorry about that. I did not even realize. Let's see. All right, homework 18 and actually, I'm just gonna hurry and mark. I've got it pulled up on Gradescope. I'm just trying to figure out which ones are included on the outline that you do not need to do.
I think it's 18 B and E.
I think so. 18B is on the. Oh wait. Oh, I see what happened. So for 3 and 4, 18B and E were combined into one problem.
I see.
And I assume that happens again on exercise 14. Let's see. 14 and 15E were also combined.
Okay.
So all the problems on the outline should be done, but you're just gonna, they might have slightly different numbers, but as long as you tag all the pages correctly, you should still be good.
Okay. Thank you.
Mhm.
Can you just repeat what questions we should combine so I can write that down?
Yeah, for sure. So it is exercises 18B and E are going to be combined. And then 14 and 15E are combined as well. On
Okay,
page
thank you.
20. Mhm.